Well, till now I used to think that coffee does not have any effect on me. It was just have I was not drinking enough concentration of coffee, and now it does have an effect on me. But whatever. So completely, yeah. I mean, my headaches are just gone. That's weird. Anyway, let's go. 41. 41 is in case of a fluid, Bernoulli's equation, Bernoulli's theorem exists the application of. Okay, fine. So just energy, right? Next question. Yeah. 42. Fountain usually seen in gardens are generated by a wide pipe with an enclosure at one end having many small holes. Wide pipe with an enclosure at one end. Huh? Consider one such fountain which is produced by a pipe of internal diameter 2 centimeter in which water flows at a rate of something. Okay, the enclosure has 100 holes each of diameter zero point 0.5 centimeters. Oh, okay, I think it's like the shower end or shower head or whatever, something like that, right? So it's just a very sophisticated shower head, basically, right? Okay. The velocity of water coming out of the holes. What is this? IDS? I don't know. Holes is okay. These extra, right? Okay. So this is the thing. This is our pipe. Right. What was the thing? A pipe of internal diameter 2 centimeter in which the water flows at a rate of 3 meter per second. The enclosure has 100 holes, each of diameter. Oh, right. So just, mass conservation. Right. So 100 holes with internal diameter 2 centimeters is 1 centimeter, right? Okay. So like pi times r squared. Oh, just the velocity. So in terms of, I just, yeah, exclude that r squared stuff. So that is equal to, so capital R squared upon small r squared. So this is diameter, okay, 0.05, it's like 0.5 upon 10, so just 1 upon 20, right? Yeah, yeah, right. So like 1 upon 20, and then you got 1 upon that. So okay, so 1 upon 40. So 1 upon 40 centimeters. Wait, okay, that's a smaller whole area. Okay, so on capital R. So actually it's supposed to be 1. So just 1 upon 20, 40, sorry. Right. And the square of these guys, right? Because pi r squared and everything. Okay, yeah, that should be the thing. The velocity of water coming out is this thing. Oh, and this has a V naught. So what is V naught? So it's water flows out at a rate. Oh, okay, they gave us the rate. That was unexpected. 3 meter per second. Wait, okay, that is the velocity. It's not the actual flow rate. Fine. So this times of 3. Yeah, that should be the thing. So although this is in centimeters and whatnot, the ratio cancels out. So it's just 40 squared. So 40 squared is like 1600 times 3, so just 4800. That means V is 48 meter per second. Right, so D is the answer. Next question. 43. This is weird. So 43 is water flows through a frictionless duct with a cross section varying as shown in the figure. Okay, pressure P at point along the axis is represented by. Fine. So it's some pressure over it. Now over here the pressure will be lower because velocity is higher. So yeah. So lower over here, higher over here, and then it's decreasing continuously. Yeah. This is weird because suddenly it's just not smooth. Doesn't make sense. C is wrong. This is also wrong. Wait, 2C option. I don't know. A is the option. Yeah, next question. 44. A cylindrical vessel filled with water up to height h becomes empty in time t naught due to a small hole at the bottom of the vessel. If the water is filled up to height 4h, it will, oh yeah, it's square root of h, right? Supposed to do that. So, 2 times t naught. Cool, which is D. Next question. It's D, not A. 45th. 45th is a cylindrical vessel open at top is 20 centimeter high and 10 centimeter in diameter. A circular hole with cross section area 1 centimeter square is cut at the center of the bottom of the vessel. Oh, okay. Water flows and this thing open at the top. Perfect. So water flows from the tube above it into the vessel at a rate of this thing. The height of water in the vessel under steady state. Oh, okay, cool. So this is what? Oh, this is volume flow rate. Perfect. Right. So our V is the square root of 2gh. Hey, we did this kind of question before, right? So Q is equal to square root of 2gh times this area, right? So yeah, cross section area, circular hole, cool. 1 centimeter square, we don't care about that. And this thing is 10 centimeter diameter. I mean, yeah, it's actually much bigger than 1 centimeter, right? Okay, square. Of course, it's bigger than that. It's like pi times of 5 centimeter square. I believe it's bigger than that. Is this wrong to assume? Well, I mean, we'll just approximate and then we'll see if something is near that. Anyway, Scott Q is equal to square root of 2gh times this area, which is 1 centimeter square. Okay, say A. Then so 2gh is equal to Q upon A. So Q was so 100 centimeter cube per second. It's like that upon this thing, just 100 centimeter per second, which is 1 meter per second. So 1 meter per second, square of that, just 1 SI units. So G is 1 upon 20 in SI units. Yeah, whatever. We don't care about that. Just 1 upon 20 meters, I suppose. That will be like 5 centimeters. So D will be the answer. Next question. 46. 46 is a fire hydrant delivers water of density rho at volume rate L. The water travels vertically upward through the hydrant and then does a 90-degree turn to emerge horizontally at a speed v. Okay, the pipe and nozzle have uniform cross section throughout. The force exerted by the water on the corner of the hydrant is. Oh, so like, fine. So once again, I'm always going to take a system which doesn't have its mass changing, right? I know you guys don't like it like that, but whatever. I'm just gonna do it like that because, yeah, it's hard for me to realize what forces are actually real and what forces are just something that we are considering like propulsion forces. What are they? They're just normal forces, but then you don't actually think of it like that. So, yeah, not going to do that. Actually, no, they're not just normal forces. Propulsion forces are in fact imaginary, right? They're not real forces. They're just because conservation momentum should happen. So that's why I'll always consider F equal to ma, never F equal to dp upon dt. Okay. So our system is of course the water inside plus this layer, okay, this pipe end of it, and it's like this. Okay, cool. So what do you want? You want the force exerted by the water on the corner of the hydrant. Awesome. Um, yeah, right. So well, think about it. There's the force because of the because of the steel surrounding it, right? So it's connected to that, and then there's this force. Okay, I mean, okay, propulsion force is the thing. In fact, not exactly what I like. So that's yeah, momentum. Okay, so that's happening, and this is also happening, and oh, think about it. There's gravity, sure, but then this is like maybe it's not important. It was vertically upward. Should we think about gravity? Well, it's not in the options, so maybe not. Right, so it's like v is in this direction. So the net F equal to m thing for this guy, like that just yeah this thing. So m dot times v in the I direction, so vi hat, and then this is like this is lost. So just negative m dot v j hat. That would be force on our system, right? Yeah, that will be the force on our system, and that's wait. Told you have like pressure stuff going on. Okay, no big deal about that. Just want the force on the pipe, not on the interesting. What if I consider that to be our system? Okay, there is pressure, sure there is pressure involved in there, and then uh, that's also gonna put some force because right. But we want just the force because of the pipe, right? Mhm. So force is by the pipe particularly. Am I missing something? Oh yeah, okay. I can do it like this thing. So this force, the actual force on the system, that's just equal to the force because of the pipe connected to the other part of the pipes. So yeah, it's that force. Okay. Plus the force because of pressures, right? So you got pressure over here, pressure over there, and because of Bernoulli's theorem, the pressures will be the same. Although this is actually down or whatever, pressures are the same. So just some pressure that we have, we don't care what that is. Uh, Yeah, well, actually, we can maybe figure that out because no, we can't. We can't. It could be anything. So just some pressure over there in terms of this cross-section area that's in the I hat direction, right? And then that's in the negative j hat. Wait, that's in the j hat direction. Sorry. Right, that's in the positive j hat direction. And then you have negative p times a I hat. That explains it. So yeah, F vector is just equal to what? So this force is the force put on by the other parts of this steel frame, pipe, whatever, on this corner, right? Yeah, and then of course, like, right. So that force is our answer, in fact, because that's the pipe's tendency to. Yeah, well, that I guess does make sense. Okay, so this will just be what m dot v minus pa times. Oh, it should be plus pa times I hat minus j hat. Okay, and right, that is the thing. Like m dot is what? M dot is just rho times a times v squared, and that's like plus pa I hat minus j hat. So forth. And we just want the magnitude, of course. So we'll just have square root 2 times the area times rho v squared plus p, right? Yeah. Now what can we do about it though? We don't know what the pressure is. Okay. Oh, we don't know the pressure actually. That's not good. Uh, yeah, we should know the pressure. Otherwise, how am I supposed to do this thing? The force is by the water on the corner of the hydrant. It is this thing. Come on, you need this much of force to keep it there, right? Oh, come on. Something. Give me something that I can. What if they just say pressure equal to 0? Okay, that would be stupid. That can't happen. P plus half rho v squared is equal to whatever is that constant. Solve the streamline. Maybe it's just equal to P not. No. No, 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 no. We don't know what the pressure is. How am I supposed to do this? It's not 0, but. Oh, God. Yeah, I mean, that is the pressure actually. So, so that's the cross section area and. What is this? What is this capital V? Oh, that's the speed. Okay. This is not looking cool. And what's this L thing? Oh, so the volume flow rate is actually L. Okay. And this thing can be like square root of 2 times rho LV plus A times P. For some reason, they're assuming P equal to 0 because otherwise this has no answer. That means square root of 2 times rho LV. That would be our answer. Really bad. This is not the answer, of course. Your answer should be this complete thing. But then, fine. So it's just D, I think. Next question, 47. I mean, yeah, that should be the thing, right? Should also have this pressure involved in there. Gravity, okay, no, just ignore gravity because this mass is not so big. Yeah. And the pressure remains the same, right? I suppose. Yes, the pressure is going to be the same, and that does it. Yeah, okay, that is the thing, in fact. This does not change its momentum, it's only this thing, and then the force by the steel parts on this thing that is what's keeping it there. Anyway, next question. So 48. Sorry, 47. A vertical tank opens at the top, is filled with liquid and rests on a smooth horizontal surface. A small hole is opened at the center of one side of the tank. The area of cross section of the tank is n times the area of the hole, right? Where n is a large number, so it's x equal to 1 upon n, right? It's 1 upon. Yeah, I thought. Initial acceleration of the tank. Oh, okay, that's different. The acceleration of the tank. Uh, Smooth horizontal surface. That's awesome. So, yeah, let's do it. And it's filled or what? It's filled with liquid completely, right? Okay. So, yeah, like just propulsion force, of course, but I don't like doing it like that. But hey, whatever. Just that's the easiest answer, so I'm gonna do that. Just m dot v, which is also just a times so rho a times v squared. Okay, yeah, that's that thing. Sure, that's the force. Now you want this thing upon the acceleration, upon the mass. So just like the density of, oh, we should actually say small a. on capital A times the height of the thing. And where is this though? Well, we don't know that, but whatever. Okay, and a upon a, this cancels. See, a upon a is just 1 upon n, so like 1 upon n, and then you got v square upon h. But you know, v square is just sort of 2g small h. Now, they are saying the orifice is at center, center of one side of the tank, right? Yeah, so this is actually h upon 2, which means this is square root of just g capital H. So square root of like just g capital H, and this would just be g upon n. That's the acceleration. Cool. So that would be C, I think. Next question. 48. 48 is two pipes PQ having diameters blah, blah, blah. Okay. Joined in series with the main supply line of water. The velocity of water flowing in pipe P is twice as that of in Q, right? Because oh, okay, no, not twice. 4 times because diameters, right? So radius is like 2 times for Q, so its area is 4 times. So it's yeah. So water flowing in pipe P has velocity 4 times that of Q. So A is the answer. That was easy actually. 49. Water flows in a cylindrical vessel of large cross-section area at a rate of 10 power negative 4 meter cube per second. Okay, so they gave us the velocity or the initial velocity, which is 10 power negative 4. Okay, if what it flows out from a hole of area 10 power negative 4 meter square, which has been punched through the base. Okay, how high does the water rise in the vessel? Oh, okay, you just want the h value. Oh, you should have told me. So just do the same thing like square root of 2gh times yeah, like this times the area, right? So small a, that is just equal to our q. So cross-sectional area of what? Oh, that didn't actually tell us. They did tell us this thing. Okay. Oh, okay, they actually told us this thing as well. Wait, it flows out from a hole of area this thing. Oh. But so this, oh no, it's not V naught, it's still Q that they gave us because it says meter cube per second, not just meter per second. So Q is this thing. Yeah, that's just the normal thing. So yeah, 10 power negative 4 is equal to the area it's flowing out from, just 10 power negative 4 as well, and then you got square root of 2gh. So h is just equal to 1 upon 20, right? So 1 upon 20 meters, which is 5 centimeters. Okay, 1 upon 20 of course. It's like 0.1 upon 4. No, 0.1 upon 2, sorry. So 0.05. 1, yeah, whatever. G equal to 9.8, maybe, who knows. B is the answer. Next question. Yeah, that's gotta be the thing. It's gotta be the thing, of course. Yeah, next for 50. 50 is a tank is filled up to height 2h with liquid and is placed on a platform of height h from the ground. The distance x from the ground where a small hole is punched to get maximum range r is, well, okay, this is something we have done a lot, right? So this is like what, filled up to height 2h, this is of 2h, okay, and h up from the ground, the distance x from the ground, okay, this is different than that. No, it's not. It's 3h upon 2 where you should have, right? So that's from the ground. Right. I mean, the whole calculation still works out. So it's, of course, at the half of the height. Yeah, it doesn't matter whether or not this is filled with water or not. Because this is what matters, right? This is water. This is the water that's doing the thing. So, yeah, just 3h upon 2. It's like 1.5h. C is the answer. So x is the distance from the ground, right? Not from the platform. Okay, next question. 51. In cylindrical vessel containing liquid of density rho, there are two holes in the side walls at at heights h1 h2 respectively, such that the range of efflux at the bottom of the vessel is same. Oh, okay. The height of a hole for which the range of efflux would be maximum is h1 h2. Oh, okay. I see what's going on. So we got the expression. The range would just be like 2 square root of capital H times. Oh, sorry. Sorry. Capital what am I doing? Small h times capital H minus small h, right? Yeah. So if these two are to be the same, there's only one way that like h1 plus h2 should be equal to capital H. So the height of hole for which range of equation maximum, that is h1 plus h2 upon 2, capital H upon 2, right? So that's D. Next question. Yeah, right. Because remember, a quadratic has only two solutions at max. So yeah, the only two ways would be like h1 plus h2 has to be capital H. Next, 52. A large tank is filled with water. Small hole is made at depth 10 from the surface. Okay, fine. The range of water issuing out of the hole is, what is this? RON? Oh, R, on the ground. Oh, what extra pressure must be applied on the water surface so that the range becomes 2R? So this is R and then you want this to become 2R. Right. Whatever. Extra pressure so that this becomes 2R. I don't exactly like this thing. Whatever. So, yeah, I mean, delta P, okay, Torsius theorem, right? Square root of our V value would just be this thing. Square root of 2 times of delta P was, yeah, sure. So just 2 times of delta P upon, because you know the thing is Bernoulli's theorem, so that's why there's 2 factor upon the density, right? That's the velocity of this gas which is showing out of it. The time period is the same. It's always just half 80 squared. Like, God, what is this height? Yeah, I mean, whatever. Does it even matter? Just capital T. We don't care what height this is. It's just, yeah, this is our range actually. So range is of this form. So for the range to become 2 times, your delta P should become just 4 times. And cool. Right. So initially, okay, at this point, your delta P is just rho G times 10 meter, right? So what should happen is that delta P should go from this to 4 times that. So the extra pressure is just 3 times of rho G H. So 3 times the density of water, right, is water, right? So 10 power 3 times G is just 10. That's what, yeah, to assume? Okay. In terms of H, so just 10 meters. That is the extra pressure you must put. Right. Yeah, extra pressure, right? So, sure, that is the thing. I suppose that would be the correct thing, right? Right? Yeah. Yes. So, this is the thing. It's just 3 times of 10 power 5 pascals. So, like 3 atmospheres. So, D will be the answer. Next question. 53. 53 is a water barrel stands on a table of height h if a small hole is punched in the side of the barrel at its base. It is found a certain stream of water strikes the ground at a horizontal distance r from the barrel. Oh, at its base. Okay, okay, okay. Right. Height h. Table. Okay, fine. The depth of the water in the barrel is. Ah, right. That is. So yeah, I mean pretty much what that was. Just we just is a sort of 2 square root of h. So our range is just 2 square root of h times the depth of the barrel. Say it's d. Yeah, yeah, yeah. Sure. It has to be the thing. It just has to be the thing. Okay. So let's figure out what d is. Yes, it's just r squared upon 4h. What's this even necessary to write down? It is b. Next question. A cylindrical vessel of cross-section area, okay, fitted with a frictionless piston of mass 10 kg, filled with water completely. A small hole is of cross-section area, something is open at a point 50 centimeter deep from the lower surface of the piston. I think it's this thing. So like you have piston over here. This is the point where a hole is opened, okay? Right. The velocity of efflux from the hole will be. And oh, so the piston has mass 10 kgs, right? Okay, cool. Its area is given, the mass is given. Yeah, I just want that, right? So use our formula, just sort of, 2 delta P upon rho. In this case, our delta P would be like 2 times of, okay, 2 upon rho. Now delta P would be, so let's say this thing is H, right? So H is equal to 50 centimeters. Just write down the things. So H is 50 centimeters, which is just zero point 0.5. Then small hole of, does that even matter? No, it doesn't. Okay. The capital A thing is 10 power 3 centimeters square, which is, okay, 10 power negative 4, right? Because sure, it's 10 power negative 1, so 0.1 in SI units. Mass, this guy, okay, the mass of the piston is just 10. G, did they give us any value? I'm not it's 10. Okay. Yeah, that's all we need, I guess. Okay, so 2, and then you just have rho GH. Oh, we also need rho actually. So the density of what is water, right? Filled with water completely. Just 10 power 3. Yes, that's gonna work out. So rho GH, okay, that's because of this guy. And then you also have the piston itself. So just, M upon A is gonna work out. So it will just be like square root of 2, and then you got GH plus M upon A times of rho. Just figure out what that thing is. So GH, this times of where is H? This thing. So just 5. Square root of 2 times 5 plus M upon A rho, which is 10 upon, what is A? Just 0.1. And so rho is 10 power 3, just 10 power 2 in that case. Just 1 upon 10, right? So 5.1 over here. So it's like square root of 10.2. Seriously? I have no idea. Why is that thing? Okay, it's close to sort of 10. So like that's 3.14 something will be close to that. So I think B would be correct. It's very weird actually. Was this correct or not? I mean, the rho is just 10 power 3. Yes, it is 10 power 3. A is zero point 0.1, right? Yeah. I'm messing up somewhere. Oh, it's mg involved, not just m. Okay, that expensive. So it's 1 upon 10. Cool, there is that, but then g is also there. So it's 10 upon plus 1. So 5 plus 1, which is square root of 12. Sort of 12, right? Which is sort of 12. It's between 3 and 4. So 3 point something, which is of course B. Next question. 54 is done. Let's go to 55. A laminar stream is flowing vertically down from tap of cross-section area per centimeter square. Okay. Distance 10 centimeter below the tap, the cross-section area of the stream has reduced to 1 upon 2 centimeter square. Volumetric flow rate of water from the tap must be about. Huh. That's weird. Okay. Flowing vertically down from the tap of cross-section. Okay, at a distance 10 centimeter below the tap. Oh, I see what's going on. But then, I don't exactly like this thing. Right. Okay, fine. So at some point, although they're saying below the tap, but then in the end, when water goes out of the tap, some other stuff also happens. Like it actually naturally decreases its cross-section area because, yeah, there is some stuff happening. But let's not go into that. We'll just assume that the tap actually is like really long, so it's actually a very big tube, and so that thing already happened, right? It's hard to explain what's going on, but hey, so what you will have to assume is that after this is out, it's already laminar and everything. Okay, so it's yeah, right. So it's as if this was in some kind of pipe, right? Although the pressure is the same everywhere, just P naught. Okay, so 10 centimeters below, your pressure is changed, and what delta P is just equal to half rho delta V squared, right? So pressure changed by how much? I mean, of course, velocity has to become bigger, right? It's like 2 times actually bigger. Okay, whatever. So delta P just rho GH is equal to rho upon 2, and then you got this thing. So like V naught. Did they give us what V naught is? No, they didn't. They did give us the cross sections though, so that's important. Right, so you can just write this like, okay, Q squared and then 1 upon area 1 squared minus 1 upon area 2 squared. That also works. Okay, So you need to figure out what Q is, and then you're good to go. So this, that, and then like 2GH is equal to Q squared times this stuff. So it's what? First is like 1 centimeter square, and now it's 1 upon 2 centimeter square. Okay. I don't exactly like this. And it's got B squared involved in it. Oof. Right. It's got to be like 2 square roots. Okay, it's just 3. I get it. It's not exactly 3. It's actually 3 times of um, centimeter power negative 4, right? Because yes, centimeter power negative 4. So what that means is like Q is just equal to centimeter square times square root of 2GH upon 3, right? Which is how much? So what is this thing? G is just 10. Then what is H? 10 centimeters. Oh God, 0.1 upon 3. Okay, which is like 0.2 upon 3. Sorry, 2 upon 3. Just 2 upon 3. And this is having weird things. So liters? Are you serious? What is this? Why is it in liters? Something's weird about this. This should not be happening. Liters per minutes? What unit is this? Okay, so it's 2/3 over there in SI units. I'm gonna do everything in SI units first of all, right? So Q will be in SI units 10 power negative 4, right? So just sort of 2/3 times 10 power negative 4. That's our volume flow rate. You want this in what? So this is what, like meter cube per second, and you want this in liter per minute. Seriously. Okay. So a meter cube is like 10 power 3 liters. This is just a square root of 2 upon 3 times 10 power 81. 10 power 81. And then you want liters per second. In 1 second, you want in minutes. So, just 60 times. Okay, yeah. 6, and then you want minutes. Cool. Which is, what is this thing? Square root of 2 times 2 square root of 3, I guess. Yeah. And that's in liter per minute, which is 2 square root of 6 liter per minute. So 2 times of, what is square root of 6? I don't know. It's like square root of 24 approximately, around 5. So this would work, I think. B. Yeah. B with answer. Less than 25, of course. So yeah, B works. Next question. Physics. Physics is a horizontal right angle pipe and bend has cross section area equal to this thing. Water flows through it at speed something. The force on the pipe due to the, once again, just very weird because they're not considering the pressure involved. We should consider the pressure involved, right? I get it. You just want like the thing with the pipe bend. The water turning, right? Yeah. But then should we not take the pressure into account? Maybe we should. Who knows? It's kind of weird. Do we take the pressure into account or not? We should, right? We should. But okay, they just want the force due to the bending of water, not really the pressure actually. So fine, then that just fits in the formula that we actually got, which is, what was the formula? I just forgot it. It's somewhere over here. Whatever. It's not derive it once again. It was like m dot times whatever velocity it has, and then you had I had and all that stuff. So just square root of 2 because of that thing, right? And then wait, what is this once again? Where's the 56th question? So wait, that's not that. Okay. Cross-section area is given. Water flows through it at some speed. Okay, cool. This is like square root of 2 times rho, and then you got a v squared. Cool. Which is how much? So square root of 2 times. What is our density though? 10 power 3 is water, right? Water flows through it, right? Area 10 centimeters square, just 10 power 84, like 10 power 83, right, in the units. Cool. And then you got v squared, so just times 400. That's the force. So 400 square root of 2. Wow. 400 times approximately 1.4, 414, whatever. Just 14 times 40. Yeah, that looks good. So, right, I mean, that must be the thing, of course. Okay, so 40 times 40 is like 560. Yeah. So 560 newtons, close to that, which is A. Next question. 57. A jet of water having velocity something and stream cross section equal to 2 centimeter square hits a flat plate perpendicularly with the water splashing out parallel to the plate. So it completely loses its vertical velocity. The plate experiences a force of, oh, okay, yeah. So this loses the force. So it is, m dot v, right? Uh, what am I doing? Just do it like this thing. Oh, this is not what I want. So dm times v. Okay, that's the thing. It's direct that upon dt. That's the force. So just m dot times v, of course. Right. Hey, do we take into account the? Well, no, I don't think we should take that into account. Should we take the actual pressure of the thing? No, 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 no. The, wait, this is weird. There is the hydrostatic pressure as well. Should we not take that into account? Because, well, that's weird. Yeah, I mean, there is hydrostatic pressure. You should also take that into account because although the whole bulk is moving with this velocity, cool, but then the individual part is actually not moving with velocity. I mean, okay, wait. I just want to shove this thing and then m dot for this guy. Won't you like want the average? So average of this thing, right? Yeah, I guess you do. And then you just want the vertical. Right, so it would be the same thing as saying, wait, what is m dot for that guy? The mass of each particle, right? Oh god, that's very weird actually. Wait, no. So the thing would be like the mass of each particle times its velocity in that direction particularly, right? And that is and you want to sum this up. Okay, so the average of this actually, right? So average of this thing. So in each dm mass, you have this thing going on. Mi times vi. You want the sum of this thing upon the numbers. Yeah. And that would actually be just the tm times v thing because turns out that I mean like we're just dealing with vectors actually. So yeah, it will turn out, of course. Correct. So yeah, it still works. This is still the formula. So our hydrostatic pressure, you don't have to take that into account at all. Awesome. Although in the last question, you actually did have to take that into account, right? Yeah. In this case, you don't have to. That's awesome, right? Or you could always go with this other thing where you just have this DM mass about to hit this, and then like it hits, and then this happens. There's like impulsive force, not exactly impulsive, but whatever. And there's also like pressure from here, right? Yeah. So like P times dt, sorry, P A times dt actually. So P A dt is the force because of that thing, and then just have this force. So that's equal to no, not equal to. It's just like yeah, and that's supposed to be happening. It's like F minus that, and that is equal to what? Wait, that's giving us a completely different thing actually because oh, that's equal to Tm times V. Oh, it should be FTT actually because that's the change in momentum that you have. So FTT. So that F is the force put on by this thing on this block, right? There is in fact pressure actually. Hey, so you do need to take the pressure into account. Huh? That's weird. But why? Why are we taking the pressure into account actually? Okay, that's the thing. These are like moving in bulk, of course. Yeah, okay, these are moving in bulk, especially because of that. So this is the dynamic. This is the dynamic pressure thing. Yes. Okay. Starting to not make sense here. Oh, some of these particles will be moving opposite, right? Okay, okay. Yeah, that's going to be the thing. Some of the particles will be like actually moving opposite to the thing, and those won't collide at all. It feels like you'll just come back or something. So doing the proper analysis, you just get this thing actually. So the pressure is in fact important. You also have to take the hydrostatic pressure into account. But then, okay, just assume your velocity is so high that that hydrostatic pressure term doesn't actually matter at all, right? Maybe you can do that. Like your velocity is as high as this could be. Does that make sense? I guess, yeah. You could do that. So this is actually giving two different things and like they are contradictory actually. Oh, this is weird. But fine, they just don't have the pressure in there, so we'll just assume it's actually not important and just think what this thing. So just m dot v. The seventh, it's supposed to be m dot v, which is what? So you have like v squared and then you got a rho. Yeah, the usual stuff. Cross section area is given, velocity is given. Right. Right, just do these things like 10 power 3 times. What is the a thing? 2 centimeters plus is 2 times of 10 power 84, and that times of v squared, which is 10 squared. Awesome. So then it's just 2 times of 10. Yeah, 20. 20 newtons or something like that. Okay, next. 58. I still don't know whether or not I should take the pressure into account. I guess we should, right? Or not? I'll think about it later. Okay, so that's done. 58. Equal volumes of two immiscible liquids of. Wait, I think I know what went wrong. No, no, no. It's actually still correct. It's still correct. It's done and it went wrong. That's not right. Okay. Ah, it's getting very weird. Okay, 58. Let's do the thing. Equal volumes of two immiscible liquids of densities rho and 2 rho are filled in a vessel as shown in the figure. Two small holes are punched at depths h upon 23 h upon the surface of the lighter liquid. From the surface of the lighter liquid, h upon 2 and then you got 3 h upon 2. Cool. Okay. If v1 and v2 are the velocities of the flux at these two, it's like proportional square root of delta p, right? So for the first guy, it's just, okay, you got 1 rho and then let's just say h upon 2 is a, right? So this is the 2, that's 1 unit. So this guy is delta p in what proportion is just 1 times of 1. Yeah. And this will have in proportion like it's 1 times of 1, but then actually plus 1 times of 1 plus 1 times of 2. So actually it's 2 plus 2, it's 4. So 1 versus 4. That's the delta p thing. So of course this will have twice as much velocity. So v2 is actually 2 times of v1. This is just 1 upon 2. So v is the answer. Next question. 59. Okay. Horizontal pipeline carries water in the streamline flow at a point along the tube where the cross-section area is 10.82 meters, where the velocity, sorry, the water velocity is 2 meters per second, and the pressure is 8,000 pascals. Okay, area is fine. Area is given, velocity is given, pressure is given. Pressure of water at another point where the velocity area is 0.5 times 10.82 is. Oh, come on, it's just Bernoulli's theorem, but with bad numbers. Okay. So this is 10.82 and that's like half of that. So we also like 4 times. Okay. So delta p is just half rho delta b squared. So yeah. What is the rho by the way? Water, right? It's just 10 power 3 in delta v squared. So initial just 2 meter per second. Now it's what 4 meter per second. So it's 16 minus 4. Yeah. Which is just 6 times 10 power 3. That is our delta p thing. And what is the pressure? It's just 8,000. So that minus 6,000 is 2,000 because now it's like faster. So yeah. So pressure at that point is 2,000 pascals. So C is the answer. Next question, 60. 60 is water is pumped from depth of 10 meter and delivered through a pipe of cross-sectional 10 power 82 if it is needed to deliver a volume of 10 power negative 1 meter cube per second. The power required will be. So pump is from depth 10 meters delivered through a pipe of cross section 10 power negative 2. Okay, the power required. Wait, but what is the? Oh, so you also have like velocity. So you have to give kinetic energy as well as potential energy to the things, right? Yeah, right. I mean that is the thing actually. So kind of like Bernoulli, but not exactly. So yeah, per second, the thing is like, so over here the energy is 0 and now it's going up, and then over here the energy is, so you have kinetic energy plus potential energy actually, and you want per second, right? So it's m dot, like okay, half mv squared versus half m dot v squared, the kinetic energy flow rate. This is very weird, this I've never seen. And then something like mgh, but then happens per second, so like plus m dot gh. Make sense? Right. Yeah, that would be the thing. Okay, so how do you get this thing? M dot is just rho av, so rho av times v squared upon 2 plus gh. Look cool. So rho a, and then this comes inside, it's just v cube upon 2 plus vgh. You know what? No, just do it the proper way. Okay, so what is the thing? Rho is just 10 power negative 3. What is the a? Sorry, 10 power 3. Area is what? So it's 10 power negative 2. Okay. And wait, they give us the volume flow rate actually. So wow, that's awesome. So like m dot. Oh, and they didn't give us the velocity actually. So fine, fine. I know what we're supposed to do. So m dot is just rho times q. And you got v squared upon 2, but then v is just q upon a. So like q squared upon 2a squared. Awesome. Plus gh. Yeah, and that is correct. So rho, what is q? It's 10 power negative 1. Q upon a, 10 power negative 1 upon 10 power negative 2. Yeah, 10 power 1. So just that's what 100 upon 2. Plus gh. H is 10, g is 10, is plus 100. Looks about right. So just, you know, 300 upon 2. Like 150 times it's just 15 times rho. It's 10 power 3. Yeah, yeah, that's the thing. Just 15 times 10 power 3 in watts, right? That's what I said. So just 15 kilowatts, which is C. Next question. Oh, actually, no next question. That's it. Wait, we do have a next question. So 61. Last question. The three water filled tanks shown have the same volume and height. If small identical holes are punched near the what? This bottom, their bottom. Which one will be the first to get empty? Okay, this will happen and this will happen and this will happen. Okay, fine. Right, so it's compared to that actually. So initially, okay, how is the flow rate going to be? It's square root of 2gh, like proportional to what? Square root of h, and then what is the thing? Square root of h, and then oh, I think I know a way you can write like it's of slope or whatever, but let's not go into that. Sort of h and upon the area of cross section, right? So that's dependent on dh upon dt. So initially this guy has bigger area, so it will have a smaller flow rate. So when is our flow rate maximum with h? That will happen when you have it's kind of weird. And a is actually like it's dependent on h, right? So a is like a linear function of h, but that thing squared, right? Okay, very interesting. Uh, yeah, now what I do? So think about it. Think about it. What's like square of that actually? Oof. So initially, you just have a high square root of h value, but then so like initially like if looks like oh this is going to be very weird actually. Yeah. Then the middle cross sections are the same, I suppose. So to get to okay this ah that will not make sense. It's like dh upon dt and they want to integrate that. first to get empty, right? Okay, so dt is proportional to this thing. So really you just want d h upon square root of h times the linear function of h squared, right? Integration of this thing. Yeah, yeah, that's what we look for. And it's from, of course, h equals 0 something. Then the linear function of h squared, like mx plus c, right? So this is the h equal to 0 part, and they have the same value at this point. It's getting complicated, right? The linear function stuff has the same value at h equal to capital H upon 2. So it's like from 0 to h, cool, but then you have capital. So at that point, it's the same area. What do you do? It's like area is, that's not the area, the radius is just equal to what? R naught, which is at the middle point, plus some slope stuff times what? Times h minus capital H upon 2, right? Something like that. So, interesting. And you could, of course, make this happen. Oh god, it's not good. Some other way, some other way. I don't want to go into the proper maths for this thing. Some other way to do this thing. Let's go into a very, very extreme case. So just, squeeze this, make this like really small. Oh yeah, okay, that would be the thing. So what we'll do is just, make the slope really, 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 really large. So then, yeah, okay. At first, it will just not get empty. Okay, so this guy, it will just not get empty at first, and then it's like, yeah, yeah. So when the h is the maximum thing, so square root of h is maximum, your area is somehow really big, so it won't work. And then when square root of h is very big, your area is small. So like this will actually be the fastest to empty according to me, right? Wait, no. We have to go for the proper method, otherwise we don't know the answer. Ah, okay, so there you go. You got the radius, right? So area will be like, oh god, pi r squared, and then, oh, not good, not good, not good. Just don't think about the pi, just think about the r squared stuff. So it's this thing, integration of r naught squared plus m, and then you got this thing. So h minus h upon 2 squared, and then you got the h upon square root of h, right? Okay, so this will be what, r naught squared plus 2 r naught m times h minus h upon 2 plus h upon 2 squared cos square of h dh. Right, so integration of this thing, right? So this integral, like integration of that, we know it's just the same everywhere. So we don't have to worry about that. Yeah. Of course, integrate from 0 to h. So yeah, we don't have to worry about this at all. Oh god. Okay, we don't have to worry about this thing. We don't have to worry about this thing. It's the same. It's the same. Oh no, we have to. It's m squared involved. Oof. It's like this thing, right? Integration of this guy. Okay, so m squared times something was this integration. And then you want plus m times. So this 2r not. Okay, this stuff, yeah, integral of that is actually the same for each of this. Like, and these are positive integrals, by the way. So just something like am squared plus bm plus some constant integrated. Okay, so that's the thing. And a and b are positive numbers. So as your m increases, right, this actually becomes, oh god, oh god, it's not going to work out. Initially h minus h upon 2 is actually, oh no, integration of this guy though. And you want this upon square root of h also, so it's actually this thing you're going to integrate. Yeah, it's positive. No, it's not. After a certain point, it's not positive. It's like when h is bigger than capital H upon 2, this goes bad, really bad. We actually have to deal with the integrals, so there's no escaping it. There must have been some other way. How can I think about it? I have no idea. Seriously. All you know is like m is positive for this guy and m is negative for that guy. That's it. That's all you know. And x is less than h upon 2. This is weird, right? This integral is going to give us negative values. So it doesn't work that smoothly. God, think about it. You'll have to deal with the integral. There's no escaping it. So then, yeah, this integral is like some kind of positive number am squared. But then you have this. Let's see what this integral will turn out to be. So that r naught is like constant. Pull that out. That's m. We don't want that. The 2 comes inside is 2h minus capital H upon square root of h. So 2 square root of h minus h and then h power negative 1 upon 2, right? Integrating this, guys, like plus 1 is 3 upon 2, so it's 4 upon 3, h power 3 upon 2, h square root of h. And going from 0 to capital H, right? So just capital H, square root of capital H, minus, so just just like, so 1 upon 2, okay. Divide by that, just 2 over there, just 2h, this sort of h, right? So just this thing. Yeah, it's negative. It's negative 2/3 of h squared of h. This is somehow negative, this integral. So just negative bm. Because r naught is a variable quantity, so we don't know what importance it has. This is the thing, right? Okay. Huh. Oh god, it's not helping. This is just not helping. So when m is 0, this thing will become like, god. I wish this was somehow 0, that would have made a lot of sense, but now it's not. So what happens when you increase m? Oh god. So after a certain point, this starts to increase. This is not going good. I don't know. I don't know the answer to this thing. You would need actual values and not figures to do this thing, right? You also have this integral which we don't care about. You have this. Okay, this is a constant. This is also constant, but it's a negative constant. That's what matters. Okay, and it's related to r naught. Okay, that's also some part of the constant actually. Okay, it depends on what r naught is actually. Yeah, yeah. We can't just say that if m is bigger than that, it's like if m is positive, then it's gonna take more time. If m is negative, it's gonna take less. You can't do that because this b thing is not positive, unfortunately. Oh no, oh no. It's going really bad actually. So I go wrong somewhere. It's like 3.2, so 4/3 minus 4/3 minus 2, right? Which is negative. It's a bit of a problem. So now that means at some certain m value, so positive m value, you have the maximum time required, and then after that actually starts to decrease, which means that you can't compare between 1 and oh yeah, right. Certainly it's not m equal to 0 at least. So it's not m equal to 0 and negative values won't work. So this doesn't make sense. So maybe the only option we have is like, okay, this is very weird. So till that point, what is happening is that, so this is the m value that you are talking about. At 0, you have some certain thing going on for the derivative, which is that it is like 2a minus b. So it's negative at 0. Okay. So at that point, you have the minimum, actually, sorry, minimum time required, right? Yeah, yeah. And so at 0, it's something, when it's negative, the time required is actually even bigger, right? Because, oh, it's not like this. This x-axis is not supposed to be there. It's time required. Come on, it's time required. It's supposed to be positive throughout. So over here, time required is bigger. So we want which of them will get empty first. It definitely cannot be where m is negative, so it cannot be second. It has to be either third or first. But then it depends. Where is first actually? Is it in this region or in this? Okay, is it in this region or is it in this region? Right? So this can't be answered, unfortunately. Okay, so it's either 1 or 3. Okay, that's it. So I think I'll see you guys in the next video. Bye.